Okay, here's segment 2 of my video. Just does 30-minute increments. Okay, so that is equal to the distance from y to x. Okay. What do you think about the third axiom? It's true, right? Mm-hmm. So in other words, if x does not equal y, then the distance between x and y is strictly greater than 0. That's the contrapositive formulation of the one part of it. And of course, the distance from x to itself is, of course, 0. So there's really two parts to axiom 3, aren't there? Because it's an if and only if statement. What about the, oh, these should be numbered 1, 2, and 3, sorry. Did you figure out if the fourth axiom works?
No, I think it does. It does not work. Did you get it to work?
I'm trying. I know what I need to show, but I haven't gotten there yet.
Okay. This one, yeah, it might actually be helpful to think backwards. What do we need to show? So you need to show, and then we'll see if we can do it or not. Maybe we can, maybe we can't. We might get stuck. So the square root of absolute x minus z less than or equal to the square root of absolute x minus y plus the square root of absolute y minus z. The question is going to be, is that true or not?
You can expand the left-hand side, and the triangle inequality holds for square roots.
I can expand.
Like add and subtract the y inside.
But then you can't split it, because you can't split square roots under addition.
You might be able to.
Right?
You might be able to manipulate it. That's why I'm stuck on.
So you're saying you want me to do that?
Which is less than or equal to the square root of the absolute value of x minus y. Yeah.
Like that. Okay, now that's definitely okay.
Can't you square both sides then?
Square both sides?
Yeah.
Of this
Square, yeah, the first one and the last one.
one? Yeah, well that's just gonna if I
Oh,
square
just kidding.
that it's fine, it's just that's gonna just tell you the usual
Right.
triangle inequality here.
Yeah. So that's where I'm stuck. I don't know how to prove that.
Well, instead of squaring both sides of this, which just leads you to your
You can square the first one.
square what's on top and see what happens
See if we can-
on both sides. So if we square this side here, this is now what I would consider scratch work because we're kind of working backwards from what we want to show. So if I square the left side, I'll have that. And the question is, if I square the right, let's see. So if I square the right side, what will I get? Absolute x minus y plus absolute y minus z plus 2 times radical absolute x minus y radical absolute y minus z. Right? So the question is that true? So let me ask you a question. Is that much of it true?
Yeah.
Just the part, the
Yeah.
part that I covered up.
Yeah.
So this part is true. So if I add more to it, it's still true.
Right.
In other words, this is not a question. This is true, right?
Yes.
So I can actually then take the square root of both sides and go back to here. So the answer is yes, this is true, and this is a metric. This does actually work. Okay, so how will we want to show that? So this is what we need to show. I'm going to actually try and write it as a proof down here. Okay, I'm just going to note that for all x, y, and z in the natural numbers, absolute x minus z is less than or equal to absolute x minus y plus absolute y minus z. That's just your standard triangle inequality for absolute value. And then I'm going to say that is less than or equal to the same exact thing, but with 2 times the square root of absolute x minus y, square root of absolute y minus z on the right side. So just add a little bit more. You have to make sure that what you're adding is positive. but this is positive, so that's fine. And now, take the square root of both sides of this inequality, so you'll get the square root of x minus z is less than or equal to the square root of this whole thing. To put the whole thing in here. Oops. Just take a little bit of care to write that out properly. And then you just have to notice that, well, what you actually have there is the square root of something squared. Okay, the thing under the radical is literally just square root of absolute x minus y plus square root of absolute y minus z. That's actually what you have there. Okay? And now you can cancel the square root from the square, and you get the square root of absolute y minus z plus the square root of x minus y. So that's it. So that's a little proof of that axiom. Does that make sense? So, you know, one of the challenges of this class is a lot of questions are sort of like yes, no, true, false. This axiom works or doesn't work. And you have to kind of think whether you think it's going to work or not ahead of time, and then this whole second part is to actually prove it as well. So you have to kind of be prepared to do both things. Okay, so this is a valid metric. If something is not a valid metric, we really can't do anything else with the problem. It's just, okay, it's not a metric, so go on. But if it is a valid metric, such as this one, we can start asking a million other questions. So I'm going to ask a follow-up question here. Okay, which is I'm going to ask you, what are the open sets? In example 1c. In other words, just for this one, I just want to know which sets would be open in the natural numbers with this metric right here. Okay, so let's think about that for a minute. What can you remind me anything you know about open sets?
For all x in the natural numbers, then there exists a p in
In the positive.
r, yeah, positive r,
Okay.
greater than 0, such that the neighborhood of x, comma p, is
It's
a
a subset
subset of x.
Well, it's a subset
Of the
of
set.
whatever the set is that you're considering as your open set. So I'm going to change this x for a minute to u. Because u, and I don't know what u is yet, we're trying to figure out what are the open sets. What could u be equal to? So for all x and u, there exists a radius such that the neighborhood of that radius around x stays inside of u. Please, guys, be very careful that you say these things in the correct order. The x has to be mentioned first and then the p. If you write, there exists, and several people have done this, if you write, there exists a p, and then you say, for all x, blah, 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 then I'm thinking, oh, you're telling me I can use the same p for every single x, which isn't usually true. Usually the p is dependent upon which point x you had considered in the first place. So it's definitely not good to be mixing these things around. Okay, be careful with that. Yeah.
Why, I mean, in the example, we're using x equal to absolute value of n. So why?
So this is my x.
I'm sorry, I don't know.
My x is the natural numbers.
That's what I meant.
Right. I'm saying which sets within x are open in this metric space. This is xd.
Right.
And then my question is, what are the, if it's a metric space, then it should have some open sets. Actually, we learned, didn't we, that you always have at least two open sets. The empty set is always open. The
Or
whole
anything.
entire space is always open. I'm wondering what else is open. How can we think about what else would be open? Just using this metric space. So Mackenzie has given us the definition of open right here. U is open just means that. That's the definition. Okay. Now there's more than just the definition that we might want to be thinking about. What do you think about when you think about open sets?
Neighborhoods.
Say it again?
Neighborhoods.
Neighborhoods. Okay, does anybody know a result that we have that connects open sets with neighborhoods? Alex?
Open sets are unions of neighborhoods.
Thank you. Exactly. Open sets are just unions of neighborhoods. So when somebody asks me, what are the open sets in a metric space? My brain goes immediately to the question, well, what are the neighborhoods? Because the open sets are just going to be unions of those. I really just want to figure out what are the neighborhoods going to look like. Okay, does that make sense?
Mm-hmm.
Now, here's my metric space. I'm going to draw a picture of it. There's one. It's just the natural numbers. It's not any of the values in between the natural numbers. Okay? So the reason I want to kind of get a picture of my set is that when I'm thinking about the neighborhoods, right? So what are the neighborhoods? A neighborhood has to be centered around a point. So, I might take a point. Let's just take this point right here, 5. Right? And think about what are the neighborhoods of 5? Like, what would they be? So, of course, it depends on P, right?
Mm-hmm.
The neighborhood is got some radius to it, and the P is sort of telling me how close the other points in that neighborhood have to be to 5 to be in there, right?
Mm-hmm.
So, we could try an example. We could say, well, what's the neighborhood of around 5 of radius 100, for example? And this would be, by definition, this is going to be the set of all little x in x, such that the distance from x to 5 is less than 100, right? In other words, it's going to be the set of points in the natural numbers such that the square root of the absolute value of x minus 5 is less than 100. It's the set of all of the points that are going to satisfy this condition. Or in other words, x minus 5 is less than 100 squared, which is actually 10,000. So it's just all of the natural numbers that are within 10,000 units of the number 5. So one of my neighborhoods would be all of these dots all the way up to the dot 10,004. Right? That would be an example of one example of a neighborhood. And of course then I have to think about unions of those. But I obviously can't list every set. I can't list every neighborhood. This is an infinite space. And this is going to be too tedious to figure every possible neighborhood out. As soon as I change my 100 to something else, then I'm going to get a different neighborhood. So I want to think about, is there another way we could get the answer here? Yeah, Mackenzie?
Well, P has to be less than the distance from 1 to 5, 1 to whatever the x is.
Let's take 5.
Okay, so 1 to 5. So it has to be.
Actually, no. P could be 100.
But
It just means. But it just means you won't be because 0 and -1 and -2. Those numbers are within the right distance of 5, but they aren't in the set. If they're not in the set, then you're not going to include them in the neighborhood. Yeah, Zane?
Any set composed of a union of singletons would be open?
Singletons is the secret to this. And we've seen this a lot, guys. We have seen this many times. If you choose a very small radius, let's take 1/2. We use that number a lot, right? Now you're talking about the set of x such that the absolute value of x minus 5 is less than, I guess it'll come out to 1/2 squared by the time I do all the algebra of it. Well, what natural numbers are less than 1/4 away from 5? Just 5, right? In other words, guys, this is the key observation. Every singleton is open. Every singleton is a neighborhood, right? So in other words, the neighborhood around any x of radius, we can just take 1/2, right, is just x itself This would be for all natural numbers x. Every singleton is open. Yes, Sarah?
Yeah, this was my answer in my mind, but I wasn't including the one because
This one?
even like, yeah, even like as much as, I mean like as a small we choose the P,
Mm-hmm.
we still can't create a neighbor.
You're not hitting
like,
the
it's not gonna
below.
be in the neighborhood.
You can create a neighborhood there. You can create a neighborhood, but take a
But-
distance of 1/4, right? It includes 1. It doesn't include anything else. It's really no.
Oh,
It doesn't
yeah.
matter because there's the next natural number. Well, there is no natural number to the left of
Mhm.
1. So there's nothing. There's no other dots inside of that interval right there. So this neighborhood just has that 1 point in it. In the same, there's no difference between how you treat this point versus any other point, actually.
Okay.
Yeah. So if yes.
So singletons are closed and open, right?
Okay, I didn't say that yet. I'm going to say that in a moment, but I didn't say that yet. So you might have another example where that was true.
Yeah.
But remember, just because something's open doesn't mean it's closed. Just because it's closed doesn't mean it's open, and including for singletons.
Okay.
Just because a singleton is open, I don't want to assume that it's closed. It turns out it will be, but it's that's kind of the next step up. I mean, if I want to know if this is closed, I really should be looking at the complement of the singleton, like everything except 5, right? And asking, well, if I took everything except 5, would that be open? Okay, so it involves a little bit more thought. But my question is, once I know that all singletons are neighborhoods, then they're all open, right? All singletons, so thus all singletons are open, yeah? And if all singletons are open, then what I would like somebody to tell me is, can you go back now and tell me what are the open sets in this example?
Any union of singletons.
Any union of singletons is still open, right? Well, if you take a union of singletons, what kind of stuff can you get?
And
The natural
any
numbers.
set in the natural numbers.
That's it. That is the answer to the question. What are the open sets? The answer is all subsets of the natural numbers. Every single set whatsoever. Okay? So, thus, all unions of singletons are open. Remember that open sets are preserved by arbitrary unions, right? Any set. So for every u in the natural numbers, every set, guys, can be viewed as a union of singletons, right? You just do this. You just write every set as a union of everything that's inside of it, as a singleton. So, U is open in X. So, as soon as singletons are open, everything is open, right?
So the complement, which is normally closed, would still be closed and open.
Right, so as soon as every subset of your metric space is open, then every subset of your metric space is also closed. Because if I want to know if something is closed, what do? I take the complement of it and I say, is that open? Well, everything is open. So the answer is yes, that is open. The complement is open, therefore the original set is closed. So in this metric space, guys, every set is both open and closed. It's the same thing as the D2 metric. The one that, is 0 if x equals y and 1 if x does not equal y. This metric basically creates the same exact topology. It creates the same layout of open sets and closed sets as if you had just used this metric instead. Right. Does this make sense, guys? So, if you're this is kind of a tough. I probably wouldn't ask a question on a test that's exactly like this because it's a little vague as to what exactly I'm looking for. But the punchline really is that I'm just trying to get you to think about singletons. First of all, I'm trying to get you to think about neighborhoods. Unions of neighborhoods are what the open sets are. So we should think about neighborhoods. And then what are those neighborhoods? Well, you know, we drew one example which was 10,000 units long. It was kind of big and hard to get our hands on, but then we realized that by choosing a smaller p, singletons actually can be neighborhoods. And therefore they're open, and once those are open, everything's open. That's really nice. Yeah, Mackenzie?
I guess I get confused when trying to think about singletons because they're confusing answers. They're always open. No.
It depends on the metric.
Okay.
So it depends heavily on the metric space. If I use the xy plane and I use the Pythagorean metric, which is the one that you're the most familiar with, then singletons are never open. Because if you try to draw a neighborhood around a singleton, now your neighborhoods look like that, and that neighborhood is not contained inside that single dot. Because now, in this case, you're using the whole R squared plane. Yeah.
Are singletons always closed?
Not necessarily.
But
No.
in Prop 5 it says...
Oh, so Prop 5, this is in section 2.
Yeah.
Let me see. Yeah, actually, for metric space, that is true. I'm sorry, yes. So singletons are always closed, my fault. Yeah, singletons are always closed, but they're definitely not always open.
Okay.
Yeah, in a metric space, singletons will always be closed because the complement of a singleton is basically almost the whole space.
Okay.
And if you're looking at almost the whole space and you pick a point in it, you can usually make a neighborhood that avoids that one point that you've deleted from the set. So. Okay, let's go on. I'm going to ask some more questions. I've got about 8 or 9 problems. We've only done one so far, but the rest of these will go faster, I think. Should be good stuff. So there, I don't know, did anybody go back and finish the group work? I didn't give you much time on Wednesday to do those 2 problems on the group work. I figured people didn't have a chance to go back to it, so I'm going to do it right now with you. Okay, this is actually a very nice problem. So true or false? By the way, on the in-class test, I'm not likely to ask you something that's like a true-false format. I'll probably say, this is true, explain why, or this is false, give me a counterexample. That's more what I like to do. Of course, if I say, is this set open or closed or both or neither, then that's kind of like multiple choice, but you still have to analyze all the cases or whatever. But I don't like to ask tricky, like true-false questions that are like very subtly dependent on the wording. But I'm going to do it here because this is just a group review session. So here's the question. If f from x to y is continuous, of course this is a metric space, so we have this statement. Can you guys remind me real quick, what's the thing that you have to remember for graduation in case I happen to be there about continuous function?
The pre-image?
The pre-image of an open set is open.
Yeah.
Awesome. Pre-images of open sets are open.
Okay.
Exactly. Great. So you guys have to get that right. You're not going to sleep the night before.
I started it wrong.
All your family is going to be there. And all eyes are going to be on you, like 10,000 people. We're going to be waiting for the answer. So anyway, hopefully it will go well. So suppose this is continuous. Now this question is inspired by that statement. If pre-images of open sets are open, then the question I want to ask here is, would images of open sets have to be open? So this is true or false. So, and I'm going to use a V instead of a U just to make sure it doesn't get confused. So suppose you start with an open set on the left side, then the question is, would the image of that open set, which would be f of V, would this be open as a subset of Y? So this is not what Proposition 8 is saying. Proposition 8 says if you start with an open set in Y, the pre-image of it under a continuous function will be open in X. Right, but this is going the other way now. So that's why we want to think about this. Do you think it's going to be true? You know, well, I should give you a little bit more time. I'm excited to tell you the answer, but I should let you think about it for a minute. If you don't think it's true, you need to be thinking of a counterexample. And if you think it's true, you need to be thinking about how you could prove it. Yeah, if you're not sure, you might just you might take something very familiar, like don't use a weird metric space. Just take real numbers with absolute value. Think of a very easy function that you don't even have to think about if it's continuous or not. You already know that it is because you've taken calculus and you just know it is continuous from there. So just choose something really easy and familiar. I'm usually, if I ever want you to give an example of something, it's never going to need to be something really complicated. Something simple would usually work. And if you think that it is true, then we have to think about how to do a proof.
Can you take a constant function?
A constant function. So define, so what's your metric space?
Real to real.
F from R to R via f of x equals 17. Does that work? Okay, let's take that. What would you like? So that's clearly continuous from Math 150A if you want, right? Constant function, definitely continuous. Okay, so we have a continuous function. Hung, can you give me an open set in the real numbers? Any open set. Is a singleton open in the real numbers? This is not open, right? If I draw a little neighborhood around a singleton, it's not going to be open. What do you think of when you think of something open in the real numbers? Do you want to say something?
Any open set, for example, we can choose 0 to 1.
You mean open interval?
Oh yeah, this is
An
what I
interval. That is what I was looking for. Just choose an open interval is open for sure, right? You could even choose, actually, if you wanted, you could choose the whole real numbers.